All right, so recall that we're talking about LP spaces. You know what LP spaces are. I have a measure space, omega f mu, and I look at the set of all measurable functions, f taking omega to r, the extended real line, f taking omega to r bar, such that if I take absolute value of f to the p, and I integrate it with respect to mu, I get something finite. The set of all functions with this property is the space LP. Here, of course, 1 less than or equal to p less than infinity. For p equals infinity, there's a different definition. Well, LP spaces are function spaces. They are vector spaces. We are on our way to seeing that they're normed vector spaces, and we will soon see that they're not just normed vector spaces, but they're Banach spaces. Okay, so of course they show up in analysis. And they show up in probability because in probability you have random variables which are nothing but measurable functions. Okay, so let me go ahead and shift to the iPad right now. I'm going to turn off the video. All right, so the iPad screen should be visible. All right, so let's see, where are we? Okay, so just a quick reminder. Let omega f mu be a sigma finite measure space. Suppose f taking omega to r bar is measurable. For p in 1 infinity, define this symbol that looks like norm fp symbol is absolute value of f to the p integrated with respect to mu, and then take the pth root. This is if p is in 1 infinity. And take this symbol, infinity norm of f, to be the infimum of k greater than or equal to 0, such that absolute value of f omega is less than k mu almost everywhere. Of course, this integral may end up being infinity, and there may be no constant k satisfying this, and so this may be infinity. So these quantities, norm fp for p in 1 infinity closed interval, these are always well defined, though they may be infinity. For any p in 1 infinity, let Lp of omega f mu be the set of all f taking omega to r bar such that f is measurable and this norm symbol, norm fp, is less than infinity. Of course, for p in 1 infinity, and here infinity is excluded, a measurable function f taking omega to r bar is an LP if and only if integral absolute value of f to the p d mu is finite. Okay, what we did last time is, this we did before that. We convinced ourselves that for any p in 1 infinity, LP is a vector space. This is done. Then we reminded ourselves last time what a norm is. A norm is basically a notion of length. Then we saw that there are 3 properties you need for a norm. Right? The third one is triangle inequality. We still have to get to that. The second one will be true quite easily. The first one requires that norm x greater than or equal to 0 for any x. That is not going to be a problem. There was a little issue with this one. So again, let's look at, suppose f is in LP omega f mu, where p is in 1 infinity. You certainly have that this symbol is greater than or equal to 0. So this first part is true. Also, if f is 0, then this symbol is 0. So if x is 0, then norm x is 0. The trouble is with the other direction. If norm x is 0, showing that x is 0. Okay, so now suppose norm f is 0. The only thing you can conclude is that f is 0 almost everywhere. So it looks like you may be in trouble, but there is a way around it. So to have a chance of making this symbol a norm, we identify functions which are equal almost everywhere. In other words, we work with equivalence classes. So if I have f, g in LP, I will say that they're equivalent if f equals g mu almost everywhere. And then I will blur the distinction between f and g. Put more technically, LP is now the set of all equivalence classes of measurable functions f taking omega to r bar such that this symbol is finite. Okay. So now the 0 element is not the function which is constant 0, but the function which is 0 almost everywhere. And so this is indeed the 0 element. And so property 1 is going to hold. Then what we did is we came up with this tool called Young's inequality. Young's inequality was used in proving Holder's inequality. What did Young's inequality say? Well, we also introduced this terminology called conjugate exponents. What are conjugate exponents? So suppose I have p, q, and 1 infinity. Okay, so note that 1 is included, infinity is included. Suppose I have p, q, and 1 infinity with 1 over p plus 1 over q equals 1. Then I'll say that p and q are conjugate exponents. Okay. What Young's inequality says is that suppose p, q in the open interval 1 infinity are conjugate exponents. And suppose I have two non-negative numbers, small x and small y. Then xy is less than or equal to x to the p over p plus y to the q over q. We went over a proof of this last time. Okay, then we stated Holder's inequality. So what did Holder's inequality say? So of course we are working on a fixed measure space omega f mu. Right? So he said let pq in the closed interval 1 infinity be such that 1 over p plus 1 over q equals 1. So suppose p and q are conjugate exponents. Suppose f is an LP of omega f mu and g is an LQ of omega f mu, then you can be sure that the product f times g is an L1 of omega f mu. And moreover, this symbol, this norm 1 symbol applied to fg is less than or equal to the p norm symbol applied to f times the q norm symbol applied to g. If I stop saying symbol, basically what this is saying is that the norm of fg in L1 is less than or equal to the norm of f in LP. And LP times the norm of G in LQ. Only problem with that is we haven't yet shown this is a norm, but it's going to be a norm. Okay, so we proved this last time. An important thing in doing this proof was the use of Young's inequality. Okay, so the next thing I want to do is something called Minkowski's inequality. What this is going to do is this is going to give you the triangle inequality for the norm. So let's get to that. Let me actually just go back and just sneak in a statement here. Okay, so this way we don't have to keep repeating it every time. So we are working on a fixed sigma finite measure space omega f mu. As the case for Holder's inequality, it's also the case for Minkowski's inequality. So let's see what Minkowski's inequality says. All right, so this is theorem. Minkowski's inequality. All right, so here's what it says. For small p in the closed interval 1 infinity and fg belonging to LP of omega f mu, we have the norm symbol applied to f plus g is less than or equal to the norm symbol applied to f plus the norm symbol applied to g. Okay, so basically this is just saying triangle inequality holds. Okay, so let's prove this. Okay, so the case p equals infinity, I will leave it to you. We'll make that a do it yourself DIY. Okay, case p equals infinity is not difficult. I'll leave that to you. So we'll assume therefore that 1 is less than or equal to p less than infinity. So assume p is in the interval closed at 1 and open at infinity. All right, so now we want to prove this thing. Right? Now this thing that I've just highlighted in blue, this is clearly going to be true if norm of f plus g is 0. Right? Because if norm of f plus g is 0, then the right side is non-negative anyway. So this inequality will definitely be true. Remember, both the left and right sides of this equation are non-negative. remember that both the left and right sides of this equation are non-negative. Okay, so if the left side is 0, then this inequality is true, no problem. All right, so result is clearly true if norm symbol f plus g equals 0. So assume norm f plus g is greater than 0. Okay, because if it's 0, then it's trivial. This norm can't be negative. All right, now let's see what's going to happen. So now, if I look at norm f plus g, this is the p norm, and I'm taking the pth power here. Well, this is going to be the integral absolute value of f plus g to the pth power d mu, right? So this is going to be the integral absolute value of f times absolute value of f plus g to the, no, actually this is not equal to, this is less than or equal to, sorry. Okay. Actually, what I want to do is the following. Let me not skip this step. Okay, so this is what I want to do. So then I'll take this f plus g to the pth power and write it as f plus g times f plus g to the p minus 1. So write this absolute value of f plus g times absolute value of f plus g to the p minus 1. Okay, and now what I'll do is I'll use triangle inequality here and say absolute value of f plus g is less than or equal to absolute value of f plus absolute value of g. All right, so you'll get this thing is less than or equal to the integral absolute value of f times absolute value of f plus g to the p minus 1 plus absolute value of g times absolute value of f plus g to the p minus 1 d mu. Any questions with this? All right, so now what are you going to do? Now, f and g are both in LP, right? Now remember here, p is in 1 infinity. Right? P is in 1 infinity. So let's find out what the conjugate exponent is. Okay. So suppose 1 over p plus 1 over q is 1. So what does this mean? This means that 1 over q is 1 minus 1 over p, which is of course p minus 1 over p. And so what that gives you is that q is p over p minus 1. Any questions with this? By the way, this formula is also true if p is 1, right? Because if p is 1, then p minus 1 is 0. And so you have 1 over 0, which is infinity. Okay. So now what do we know? So we know that integral absolute value of f plus g to the p. I'm not going to keep saying d mu. All integrals are with respect to the measure mu, so no need to say that. So this thing is less than infinity. But let's see what this is. But integral absolute value of f plus g to the pth power equals integral of absolute value of f plus g to the p minus 1 time to the power p over p minus 1. Okay. Why is this true? This is true by laws of exponents. Okay, I think as we're going through this, I think that there may be some subtle things going on if p is 1. Okay. So here, let me take care of the case p equals 1 later. So suppose p is in 1 infinity. Okay. All right. Let me just backtrack a little bit just to make sure that we're all on the same page. Both f and g belong to LP. P is in the closed interval 1 infinity. The claim is that the norm of f plus g is less than or equal to norm of f plus norm of g. That's what we want to prove. Okay. I claim the case p equals infinity is not difficult, and I'm leaving it to you. Do it yourself. So, assume that p is in 1 infinity, where 1 is included but infinity is excluded. Now, first statement is that if the left side is 0, then the inequality is clearly true because both sides are non-negative. So assume that norm f plus gp is greater than 0. Now what I'll do is, I'll take norm f plus g pth norm to the pth power, and as I go along here, maybe I will let me move this a little bit. Okay, let me put that there. All right. So these calculations are all okay. But now what I'm going to start to do is I'm going to start looking for this conjugate exponent q, right? So now here, let me suppose that p is in the open interval 1 infinity. Okay. So in this case, I'll find the conjugate exponent q. Q is going to be p over p minus 1. Now again, remember I'm taking a p in the open interval 1 infinity, so q is going to be finite, by the way. Okay. All right. Okay, so now what do you have? You have that integral absolute value of f plus g to the p is finite, but integral absolute value of f plus g to the p is nothing but integral absolute value of f plus g to the p minus 1, the whole thing to the p over p minus 1. Right? This is just laws of exponents, and this is finite. So what is this saying? Thus, it is saying that this function on the inside here belongs to LQ. Because when you take its qth power, remember that q is p over p minus 1. Okay, so q is p over p minus 1. We have checked that. This inside function, when we take its qth power and integrate, we get something finite. That means this inside function is in fact in LQ. Thus, the absolute value of f plus g to the p minus 1 is in LQ. All right. Again, I don't need to specify which measure space we're working on. Everybody knows that. So now I'll use Holder's inequality. Okay. Okay, so using Holder's inequality, what do you get? So, okay, so where am I going to return here? I'm going to return to this equation star, right? So what am I going to say? I'm going to say this guy is in LP. This guy is in LQ. We have just shown that. So the product is going to be in L1, and we can upper bound it using Holder's inequality. Similarly, this guy is an LP. This guy is an LQ. We have just shown that. So again, this thing can be upper bounded using Holder's inequality. So in equation star, we will upper bound things using Holder's inequality. So let me write down this equation star again. Norm f plus g p norm to the pth power is less than or equal to integral absolute value of f plus g to the p minus 1 plus absolute value of g absolute value of f plus g to the p minus 1. Okay, and as we just discussed, this guy is in LP, this guy is in LQ, this guy is in LP, this guy is in LQ, and so their products are in L1. Okay. Is that my computer? Okay. And by Holder's inequality, we get, well, the left side stays the same, norm f plus g. This is the p norm to the pth power less than or equal to. Now here, what am I doing? I'm going to get the p norm of f times the q norm of absolute value of f plus g to the p minus 1. Okay, this is just Holder's inequality applied to this first part, this first integral. Okay, and again, for the second one, you have a similar Holder's inequality. So this is going to be plus the p norm of g, and then I'll have the norm of absolute value of f plus g to the p minus 1 in LQ. Any questions so far? All right, now basically let's find out what this thing is. Okay, note that the same thing shows up here and here. Let's find out what this is. Now, if I look at absolute value of f plus g to the p minus 1 and I look at its q norm, what is that going to be? Well, to get the LQ norm, you should take the qth power, integrate, and then take the qth root. So I will take absolute value of f plus g to the p minus 1. Then I will take its qth power, so I'll multiply by q in the exponent. Then I'll integrate it with respect to mu, so I won't repeat that it's with respect to mu. And then what I'll do is I'll take the qth root. And now you remind yourself that p minus 1 times q, this is just p. This we had on the last page. So this is going to be the integral absolute value of f plus g to the p, all to the power 1 over q. Okay. So what is this? This is the integral absolute value of f plus g to the p, all to the power 1 over q. What is 1 over q? 1 over q is p minus 1 over p. So this is going to be p minus 1 over p. All right, so now what I'm going to do is the following. I'm going to write this as integral absolute value of f plus g to the p, all to the power 1 over p, all to the power p minus 1. I can do this. This is just laws of exponents, okay? And now I stare at the thing inside the square brackets and I realize that, oh, this is simply, what is this simply? This is simply norm f plus g p. Okay, so what do I get? I get this thing equals norm f plus g p to the p minus 1. All right, so now I'm going to plug this back into this equation. Should we give that equation name, number? Okay, let me just highlight it. When you plug it into the highlighted equation, what you're going to get? You're going to get a norm f plus g lp to the pth power is less than or equal to norm fp times norm f plus g p to the p minus first power, right? Plus norm g q and norm f plus g. No, not q, my bad, sorry. It's not q, it's p. Norm f plus g p to the p minus 1. All right, and now you can see what's happening here. On the right side, you have this common factor. So you want to divide both sides by it. So on the left side, you have norm f plus g to the pth power. On the right side, you have norm f plus g to the p minus first power. So you want to divide both sides by norm f plus g to the p minus 1. This is why you have to assume at the beginning that norm f plus g was 0, was positive, sorry. So dividing both sides by norm f plus g to the p minus 1, what do we get? We get norm f plus g p less than or equal to norm f p plus norm g p. All right, because what is going to happen is that this is going to disappear. And when this disappears, from this p, p minus 1 is going to disappear. So what's going to be left is just 1. Okay, and this is what you get. Okay, so actually, if you want, let's just write one more line here. So this is what this is: norm f p plus norm g p, and the whole thing times norm f plus g in lp to the p minus 1. Okay, so this looks a little clearer. Okay, so now you divide both sides by norm f plus g to the power p minus 1, and lo and behold, you get this, which is precisely the triangle inequality. All right, so let's take stock of where we are. We have shown that LP is a vector space. That is done. We have defined this norm symbol, and we're almost there to showing that it's a norm. We've taken care of the first requirement for norms. We did that by identifying functions which were equal almost everywhere. We've taken care of the third requirement for norm, which is triangle inequality. So the only thing that's left is to check that norm of alpha x is absolute value of alpha norm x. That's all that's left. And let's just wrap that up also. Oh, by the way, one thing that was left was the case when p is when the case is not when p is 1. And this is actually quite straightforward, because what I'll do here is, so basically I'll get norm f plus g in L1. This is the integral absolute value of f plus g, right? But by triangle inequality, this is less than or equal to integral absolute value of f plus integral absolute value of g. But wait a second, what is integral absolute value of f? This is simply the L1 norm of f. And this is simply the L1 norm of g. And so, yes, even for the case p equals 1, it's quite trivial. All right, so now we have covered everything except the case p equals infinity, which has been left for you to fill in. Any questions? Okay, now the last piece to conclude this whole business, that this thing that we're cautiously calling a norm, is the following. So consider LP of omega f mu equipped with this symbol, and P is in the closed interval 1 infinity. Okay. Now clearly, norm fp is greater than or equal to 0, and norm fp equals 0 if and only if f equals 0 mu almost everywhere. Okay, so basically this is saying that f belongs to the zero equivalence class. All right. The second property of the norm is quite easy to check. I will leave it to you to do this. For any alpha in R, I leave it to you to check that if I take the P norm of alpha F, I'll just get absolute value of F times the norm of P. Okay, so this is a straightforward thing. Let me just leave it as a do it yourself. And finally, the Minkowski's inequality. The Minkowski's inequality norm F plus, okay, F plus G P less than or equal to norm F P plus norm G P whenever, okay, so actually let me do the following. So now for finding a Minkowski's inequality for Fg in LP of omega F mu P in 1 infinity, we have, okay, so we have this thing. This is the Minkowski's inequality. So the thing that we've been calling a norm is a norm. So thus, this symbol is indeed a norm on LP of omega F mu. And let's just for emphasis say where we have identified functions which are equal almost everywhere. Okay, which are equal mu almost everywhere. All right, so lo and behold, okay, by the way, now let me just so when I say P norm or LP norm, I'm referring to this symbol. Okay, so if you hear me say the P norm of F, I mean this symbol applied to F. If I say the LP norm of F, I mean this symbol applied to F. Okay, so this norm we call the LP norm or the P norm. Okay, any questions? Okay, so now that so what do we get? We get so this thing is a normed vector space. And of course, a question that arises, given that it's a normed vector space, is that is it complete? Well, what do I mean by complete? We know that a metric space is complete if every Cauchy sequence converges. Now, if you're in a normed vector space, that is a metric space. The distance between 2 points is simply the length of the vector, which is obtained by taking the difference of the two things. And so, of course, you can ask the question, is LP of omega F mu together with this norm complete? In other words, do all Cauchy sequences converge? And the answer is yes. So it turns out that LP of omega F mu is complete. I.e., whenever we have a Cauchy sequence Fn m going from 1 to infinity in LP, this sequence must converge. So there exists f in LP such that norm Fn minus f in LP goes to 0. All right, any questions so far? All right, so I want to do some of this part of showing the completeness of LP. I will not do it in entire detail. By the way, let's just note the connection with probability before we go any further. Okay. So note so that if omega Fe is a probability space, well, of course, there's a special case of a measure space, right? So all the LP stuff applies. So then the foregoing LP spaces facts apply. Facts and notions apply. In other words, you can still talk about LP spaces here, of course. Right? The notation may be a bit different. And just let's give an example of this. So for example, for 1 less than or equal to p less than infinity, a random variable capital X, which is of course just a measurable function defined on omega Fp, is said to belong to LP if, okay, let me, since this is the first time I'm doing this, let me write to LP if omega Fp if expectation absolute value of x to the p is finite. And of course, in this case, what is the norm going to be? So the norm x in LP is going to be expectation absolute value of x to the p all to the power 1 over p. All right. Okay. So of course, the LP stuff totally applies to probability spaces. The notations may be a bit different. Instead of integrals, you will see expectations. Instead of measurable functions, there will be random variables. Instead of writing them as f, you may write them as x. Okay. But all the material you saw still applies. All right, so where do I want to pick up? Yes. So now I want to just tie up a few loose ends, and this has to do with the completeness of LP. Okay, so I basically want to do part of the proof that LP is complete. Okay, so here's the idea. What I'll do is I'll first we'll just talk about what it means for. Well, we already know what it means for a non-vector space to be complete. Then we'll introduce this definition as to what it means for a series to converge and what it means for a series to converge absolutely. Okay, then there is a theorem which we will just state, I will not prove it here, which says that completeness is the same as every absolutely convergent series is convergent. We will just state that, we will not prove it, I'm sure you have seen the proof. Then we will use that to show that LP is in fact complete. So that's the order in which we're going to go. Okay. So let omega f mu be a sigma finite measure space. Right. We know that for small p in the closed interval 1 infinity, LP of omega F mu together with this symbol is a normed vector space. All right. We want to show that this normed vector space is complete. So to do that, let's just remind ourselves of a couple of things. So here's a definition. This definition that I'm writing, this you will have studied. This is not new. Okay? So let V, comma this norm be a normed vector space. All right. So now, if I have a sequence small xn, n going from 1 to infinity in V, then the series summation n going from 1 to infinity xn is said to converge to x in V if the sequence of partial sums converges to x. Okay, so if the sum n going from 1 to capital N of small xn converges to x as capital N goes to infinity. Right? In other words, the sequence of partial sums converges to the desired limit. Okay, this is not new. Okay, this is something you have learned since the beginning of your BSc. By the way, now you may suddenly ask, oh, what does it mean for this sequence of vectors to converge to this vector? Well, it means that if I take the norm of this minus this, then that goes to 0 as capital N goes to infinity. So let's just make a quick note of that also. i.e. Limit capital N goes to infinity of the norm of the sum n going from 1 to capital N xn minus x. This is 0. Okay, so this is once again a reminder. Now, what does it mean for the series to be absolutely convergent? Here's what it means. So the series sum n going from 1 to infinity xn is said to be absolutely convergent if the sum n going from 1 to infinity norm of xn is finite. Okay, of course, if a series is absolutely convergent, I may also say the series converges absolutely. It's the same difference. All right, now this whole thing, let me just, this whole thing is something you have learned before. Okay? So this was just recalling a few things that you've learned. All right, so now here is a fact. Then this basically gives us a way to show that a normed vector space is complete. I am going to state this. I am not going to prove it. The MA514 notes have been shared with you. And in the MA514 notes, you will be able to find a proof of this, if you like, on the back of page 27. Okay. But anyway, so I'll just state a theorem which we will use but not prove. So here's the theorem. So a normed vector space V together with this symbol is complete if and only if every absolutely convergent series in V is convergent. Okay, so that means if every absolutely convergent series is convergent, then the vector space is complete, or normed vector space is complete. And if the normed vector space is complete, then every absolutely convergent series is convergent. I will not prove this. You can see the NF514 notes for a proof. All right, however, we will use this, okay? And we will use this to show that LP is complete. Now again, as you have already probably started to smell, the arguments are sometimes a little different depending on whether P is finite or infinite, right? So here also, once again, I will do the case when P is in one infinity, and the other one I will leave it to you to fill in. Okay. So here's our theorem. Okay. So for 1 less than or equal to P less than infinity, the normed vector space LP of omega F mu together with this LP norm, this thing is complete. Okay, I'm not going to say again, but we are working on a fixed sigma finite measure space omega F mu. So let's prove this. Okay, note that in this statement, we only looked at the case where 1 less than or equal to P strictly less than infinity. Let me leave that highlighted. The claim is also true for P equals infinity, but I'm not going to go through it. All right, so let's prove this. So it suffices to show that every absolutely convergent series in LP is convergent. All right, this is based on the theorem that we stated, but we did not prove. Okay, so let's start with the series which is absolutely convergent, and let's try and prove that it is convergent. Okay, so that's what we need to do. We can do that, our job is done. So let Fk, k going from 1 to infinity, be a sequence in LP such that sum k going from 1 to infinity of the P norm of Fk is finite. Okay, i.e. the sum k going from 1 to infinity Fk is absolutely convergent. Right, a series is absolutely convergent if whenever you take the norm of all the summands and add up the resulting numbers, you get something finite. Okay. So what we want to show is that, so what we know is that this series is absolutely convergent. In other words, if you take the norms of each of the summands and add them all up, you'll get something finite. But what we want to show is that the series itself is convergent. Really convergent. Okay, so we want to show that this series sum k going from 1 to infinity Fk is convergent in LP. Oh, so what does that mean? If I say it's convergent in LP, that means there exists some function in LP to which this guy converges. So what do we want to show? I.e. there exists and here I'm going to use capital F in LP such that some k going from 1 through capital N, small fk minus capital F in LP goes to 0 as capital N goes to infinity. And that's what you want to show. You want to show that this series is convergent in LP. That means you want to show that there is some function such that the sequence of partial sums converges to that function as n goes to infinity, and here convergence is being measured by taking the difference of these two vectors and subsequently taking the p norm. Okay, so this is what we want to do. All right. So here's what we'll do. So let B equal the sum k going from 1 to infinity norm fkp. Now remember, this is finite. Okay, so B is the sum of the norms. We already know this is finite because we know that the series is absolutely convergent. All right, so now what I'll do is let capital Gn equal the sum k going from 1 through n, absolute value of fk, and then I'll let capital G be the sum k going from 1 to infinity, absolute value of fk. Okay, before I go any further, is there any danger that this quantity may be undefined? Okay, spoiler alert, there is no danger that this quantity is undefined. Why is there no such danger? What sort of sum is this? It's a finite sum, so there's no danger of Gn running into any problems with Gn. Okay. Now, I have shamelessly written this here. And you may say, why did he just write this and he was not sure that this guy exists? Okay, so remember here, when we're talking about this thing in green, this function is quite well defined, right? Why is it well defined? Because I'm taking all the absolute values, right? I'm taking absolute value of fk. I'm taking absolute value of fk. This is a non-negative measurable function, and I'm adding up a countable number of non-negative measurable functions. So this is well defined and measurable. Worst case that will happen is that this is infinity, but there is no danger of running into infinity minus infinity. Okay, let me make one quick observation and then we'll stop. Note that Gn increases to G. You know what this means? This means that as I take the limits as n goes to infinity, pointwise Gn converges to G. Okay, I think we're already at 4:01, so let me stop right there. Any questions?
Sir, can you share the notes after the assessment?
Oh, yeah, I will share the notes, yes.
Thank you.
I'm going to stop recording now also.